Hi there, it's me again. It is Wolf Dynamics with another video of how to set up turbulence simulations now using the reference case of the flat plate. So we have addressed so far 4 turbulence models of the K omega family. Okay, now let's move to another simulation type. So let's do DNS or laminar. Okay, so we don't have it in the list here. Let me move here because that enters into classified into SRS. So this is what we're going to do: laminar DNS, direct numerical simulation. Okay, so you know that the stuff here, fully three-dimensional, totally unsteady. You need extremely fine meshes, but let's try to run something. Let's say if it crashes, if it doesn't crash, or if we get something, what do we get? So let's move on to address a little bit the theory. So when it comes to the theory, this is what we're solving, the exact Navier-Stokes equations. And to be more precise, okay, as we are working in compressible case, this is what we're solving. So look at that, we are solving here every scale, no? The DNS, the famous or infamous DNS, direct numerical simulation, fully three-dimensional, fully unsteady. If you want, or if no, you must solve all scales, Kolmogorov scales. That requires extremely fine meshes, very high computational cost. So you need good computers. Okay, this is what everybody wants to do. Okay, but it is difficult and it's limited in the Reynolds number. So here there is no modeling. This is the easy simulations that you can do. Okay, so this is the only thing I can show you. Now we don't do all that treatment as in the Reynolds stress or less or whatever. This is what we solve. Okay, nothing to add, no model. So from the modeling point of view, a little bit more relaxed in the sense that no coefficients, nothing to take care for if you want to model some scales. So let's go and run the simulation. So here we have the case. So this is the laminar model in OpenFOAM, and any software they're calling laminar or something else, I don't know. In Fluent, I recall it's called laminar, CFX also laminar, and if we well recall, the StarCCN also call it laminar. Okay, means that you are not adding any model. So here you have the case. As usual, high re, low re. In DNS, it makes absolutely no sense a high re. You know that you need to solve all the scales. So I will go directly here, and we already have a solution here. Okay, so I'm not going to go into too many details. I'm going to rerun it just to show what we see in the screen. But boundary conditions, UMP, that's all. You don't need any K omega X and nothing else that. Okay, UMP, you set standard values, so you see it's super easy to set up. No need to compute estimates. Then physical properties, well, it's always the same. You go here, put laminar, and that's all. Okay, will be a DNS. If your mesh is not fine enough, it will be an under-resolved DNS, or I don't know how to call it, will be a completely wrong simulation, like in this case. Okay, so basically then we go to the numerics. So control D, as usual, you have everything. So here you don't have any models, so these temporary objects, nothing to get there when it comes to turbulence, but there is a lot of stuff passing there. And let me just put here that just to show you that there is a lot of stuff. Then SV schemes, nothing to do, just this stuff is not being solved, even though I have it here, it's not being solved. And SV solutions, well, standard one as usual. Okay, so as you see, it's setting at DNS. Okay, it is the simplest things that you can do. They tend to always run to give a solution. So sometimes you will see that I run my turbulence simulation with a turbulence model. I don't get a solution, it diverges, but mainly because it shows the wrong values. In laminar, it will always run but your solution. If you don't have a super fine mesh, your solutions are always wrong. To mention here that what we're doing here is even worse because we're doing a steady state, okay? So it's even worse. We already have a quartz mesh, and then we add this hypothesis steady state. So it's super wrong, but let's see what we get, okay? So I added the low re And let me here run the mesh, okay? And then phone run. And look at that, it's running. And these are, remember, we don't have any model. And look at that, we have in cache all this information. So now this stuff is related to gradient, matrices, whatever. So very interesting information that you have here. So if you want, you can save this data, identify some specific of this object, specific objects, and then visualize that information in ParaView. And maybe you might be interested in some other objects there, but this is what you get. So in that case, you will need to go directly and modify your sources. So for instance, sometimes I am interested in getting where your slope limit in SVSkin, you have this load limiter, the gradient limiters, where those limiters are being switched on or where they are actually acting. So that information is not safe here, or at least I haven't identified that here. So I modify my source code to save that specific field. So that is just general knowledge, okay, just to show you that. And let's go back here and comment that. And let's run the case, okay? So you will see that everything is going to run smooth, okay? You have just UMP, nothing K omega. And let me go here also and icon the 2 Python plot washer, lot solver, and plot now the residuals here, and everything is super smooth, super nice. And people always say, okay, I run my laminar case, okay, and I know that the simulation is an industrial one, that the flow is turbulent, and I get a solution. But if I run using a turbulent simulation, a turbulent model, I don't get a solution, okay? So be careful about that. Laminars are always run, okay, unless you get a superfine mesh. So enable your turbulence model, and it's about choosing the right boundary conditions, initial conditions, right numerics. So at this point, let's wait for the final result and then discuss the solution. Okay, so we reached the end of the simulation, and there you go. Everything is smooth, nothing is strange, running the case. So look at your values, and if you pay attention to the y plus value, and if you recall previous simulations that the average value was higher than this, if I will recall, look at that here, it's much lower. Kind of, it's already telling you that things are being under-predicted, probably, as we're going to see later. So there you go. Now we run, everything runs smoothly. And now let's do the post-processing, okay? So Python built in. In this case, we have only one state in ParaView because we don't have K, nothing, so don't need to open the other. So we have ParaView, one state. Okay, and there you go. This is our solution. So you can take a mental image of the other cases and you can compare, and you will see that there is a lot differences there. So let's take a look at this plot. So the dashed line represents where our actual solution, and see that we have a fantastic fitting with the viscous law. Okay, look at that, it's following precisely that. So this is telling you one thing. The only good thing that is telling you here that, okay, you are resolving well the viscous law. However, as the flow, we know that Reynolds is 10 million, it is turbulence, should be doing this blending and then going into the turbulent regime. But in this case, it is remaining laminar. You see here, following that laminar behavior. And you see this behavior, this reflected into the friction coefficient. So see that red represents your current friction coefficient computed here in the wall, and see that is highly under-predicted. So you see here a run. So all the previous cases that are correct, here now we see a run behavior, okay? But because we didn't enable that model. So by enabling a model here, you're going to get a correct result. Even if you use the Prandtl model, that is an algebraic model, you are going to get the correct results because that model works for this case. So yeah, this is it, okay? So if you would like to get the right results, your mesh will be something very, 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 very fine. So You need to have a lot of computational resources. And to mention something that also the post-processing for the high res, that it makes no sense a high res in DNS Laminar, and see that we get here that the results are wrong and incorrect. Here, look at that, you're starting from here. Now in this case, see that the y plus is something about probably 80, but it's just mashing. It is mashing all this correlation, the viscous law. So yeah, there you have. If you want a DNS, this is a DNS. It is a completely wrong, but it is a DNS. No modeling at all included. So yeah, with this, I conclude this, and let's go here that we're just here crossing the models, and now let's cross this one as well. We're going to revisit this one because we need to revisit actually, but for the unsteady cases, but the results are going to be wrong as well. Okay, so now we address 4 k omega, okay, 4 punks here, and now we have all this culprit here as well, okay. And in next videos we're going to switch. Now we're going to go back to actual turbulence modeling, so we're going to see this parallel models 1 equation, and then we visit all the k epsilon models. So hope you're enjoying this, and see you next video. Bye.